All right, good morning, everyone. Hello, DeepSec. I heard you liked your security deep, so we're going to go about as deep as you can possibly go on the x86 platform today. Not stopping at virtualization layer. We got to keep going down lower BIOS, right? So, I'm Zeno. These are my colleagues who I work with. We consider ourselves to be trusted computing researchers. So whereas trusted computing has a bad name a lot of places, we are unabashedly for trusted computing. Why? Because your computer architectures are fundamentally and architecturally insecure, and if you don't start adding security back in, you get, insecure things, and you get to live with the lack of security forever, right? And if that's what you want, then go ahead and keep opposing it. But if you want to actually have some security, you need to start fixing the architectures. So I work at MITRE. MITRE is a not-for-profit company, so it's a corporation, but it's a not-for-profit company. And all we do is we run federally funded research and development centers for the U.S. government. So the basic point there is Congress sets aside some money, and they say, okay, well, we know that the majority of the work for the U.S. government is done by contractors. They have a profit motive. Their goal is to get the government to buy some more of their stuff. And MITRE is set aside as sort of, MITRE and other FFRDCs are set aside as sort of neutral, independent advisors. MITRE's been around for quite a while. Back in the ARPANET days, the .org was set up for MITRE because we're not military, we're not government, we're not commercial, we're not educational, and we're not, an ISP. And if you've heard of MITRE, it would only be through things like some of the standards that we've done, CVE, the most notable one, but CWE, weaknesses, MIC, malware attributes, stick syntactic, threat intel. But we don't advertise, it's not like MITRE's CVE, it's just CVE. So even still, I wouldn't necessarily expect you to hear of it because, again, we're not commercial, we can't work for you, so we're not out here advertising anything. We're just talking about our research. So today, I would like to tell you a dark fairy tale. The following is fictional and does not depict actual events. So, once upon a time, off in Neverland, and I'm going to have to read this verbatim because I haven't memorized this still, but there once lived a mighty dragon named Smite'em the Stealthy. Unlike some of the more bombastic, persistent, and advanced dragons of the day, Smite'em was a devious fellow. He took great pains to hide himself, make sure that those he stole from never knew that he even existed. For many years, Smite'em was able to prey upon helpless villagers, stealing their treasure for himself without them ever even knowing he was there. Then one day, a great and mighty hero, Copernicus, came to those lands. He was a man of science. He believed in an evidence-based approach to understanding the world, and wherever he went, he told people to question their assumptions. He knew that in the darkness of ignorance lay dangers, and indeed he formulated a hypothesis that despite the fact that his instruments were unable to detect it, surely some devious creature must lay behind the mysterious thefts that plagued that dark land. Good Sir Copernicus resolved to enhance his senses with new and more trustworthy technologies. That way he would not be deceived like so many others were before him. And lo, did Smite'em appear before Copernicus too. And they did wage a furious battle of wills. The great worm writhed and thrashed, its belly filled with fire at the outrage of its discovery. And for a time it did seem that Copernicus too had won, and there was much rejoicing. Yay! And that brings us to today. For you see, the battle between Smite'em and Copernicus awoke another dweller in darkness, the Sandman. He saw the power that Copernicus too wielded when triumphing over Smite'em, and he coveted it. He resolved to harness in himself the might of both beast and man, for he knew of another terrible lizard that had mysterious powers, the mighty Charizard. There we go. The couple of you who chuckled, you're young. Yes, indeed, the mighty Charizard was a beast that had a penchant for attacking the very core of all that you hold dear, your computer's firmware. So begins the tale of the Sandman, the once and future king. So, although the preceding was not based on any previous events, it's actually, so what am I talking about? I'm talking about our existing work. So that's our past work and our current work that I'm going to be talking about today. So last year at Black Hat, we showed a variety of problems down in trusted computing technologies at the lowest level. You use it, but we want to also assess it, make sure that it actually works the way people say it should. Because, it's all nice to have an architectural specification, but we all know that always between specification and implementation, problems arise, right? So we checked the implementation of some trusted computing stuff. We said, hey, this is broke as a joke, but B, we can build a new, more trustworthy version of things, and C, if you're not going to run our custom BIOS in order to build a better sense of whether or not you're compromised, you can use this other tool called Copernicus. So Google MITRE Copernicus, and you'll find a free tool that you can download on Windows. It only supports Windows 7 and newer at the moment. We're adding backward support for XP. Hopefully none of you are running XP, but it was more we wanted to catch the Windows Server 2003 and newer. So Copernicus was basically a way that instead of having to run a custom BIOS, you could come from within a system and you could try to check and find out whether or not the system is actually infected. But at the time, we knew that, there were potential ways to get around Copernicus. There's ways around everything, right? But at least, you need to know them. So at CanSec West earlier in the year, we described a thing called SMITEM, the SMM man-in-the-middle attack. And this is sort of an architectural attack where you can basically defeat any sort of software BIOS capture mechanism like Copernicus, Flash-ROM, ChipSec, anything out there right now. So we said, okay, well, we're not kind of people who complain about stuff without actually providing a solution as well. So if the trusted computing technology is broke, then we provide a better way of doing things. If the BIOS checking is broke, we provide a better way of doing things. So we released Copernicus 2, also available for download. And the point with Copernicus 2 is we utilized Intel TXT, trusted execution technology, in order to try to build software that was vulnerable to less subversion, and specifically software that could defeat SMITEM. And then shortly thereafter, at Syscan, we disclosed another vulnerability in BIOS access control mechanisms. Throughout the last couple of years, we've been, the more we look, the more problems we find, and that's kind of the way things go, right? If nobody's looking, nobody's vetting and getting rid of problems. So we found an access control mechanism that would enable us to bypass this BIOS lock enable bit, and I'll talk about all that a little bit more later. And we put out a proof of concept for that called Charizard, so that's where the Charizard comes from. And it was called Charizard just because Sam Cornwell is our junior member of the team, and he's young, and he didn't come up with a better name for it, so he gets stuff named after Pokemon. So in this talk, we're going to talk about the Sandman, which the one-line summary of the Sandman is do a Charizard attack with TXT. All right? So there you go. If you already know Charizard, if you've already seen our related work, then you're done. Go away. If not, I'm not assuming that you're all following us with your rapt attention. So we're going to sort of explain the minimal amount of those previous talks that we have to in order to get you to the point where you can understand the Sandman attack. But I wanted to put up front that part of our motivation for pulling this out and making it its own attack is, Invisible Things Labs did a lot of good work back in the day. And we said, we modeled ourselves on them. We said we must be, this tall or taller. We must be this lead or leader. So amongst their many talks, they defeated things like TXT. They defeated things like BIOS security. In one of their talks where they were talking about AMT, active management technology, they made this little note. They said, well, AMT is extra bad because whereas, we've got these other security technologies, we've got, virtualization and IOMMU and trusted execution technology, you may be able to bypass those, but at least they shouldn't theoretically help the attacker. Now, that's a strange statement coming from them, given that Joanna Rakowska's big, publicity push was around, well, this virtualization will definitely help the attacker and make virtualized rootkits, right? 2006. For those of you who can't Google and find other citations, right? 3 different virtualization rootkits came out in 2006. So anyways, they said, well, those things can be bypassed, but at least they don't help the attacker, right? So we wanted to make it clear, everything's pretty much a double-edged sword, so we wanted to show an example of TXT helping the attacker. We used it for Copernicus too, because we like it, and we like to have more secure software. But we wanted to be clear, you have to still know how this can help an attacker, and you have to work around that. Because we don't want it to be the case that you go out and use Copernicus too, and make yourself vulnerable to the Sandman. So, when we did our Black Hat talk, we're saying, okay, here's our proof of concept malware, various things that can infect the BIOS and lie about the trusted computing state and say that you're trusted when you're not. And we said, here's Copernicus. And so people naturally said, okay, well, can your Copernicus detect your tick and your flea malware? We said, yeah, I can detect the tick and the flea, but it can't actually detect everything. So we know of alternative means that you can get around it. So we put Copernicus out there to be just sort of a best effort, like, okay, well, there's nothing right now that you can use to inspect your BIOS, so let's throw this out there, and then you can start actually checking. And, Dragos went out there, and you'll see the tweet by Dragos saying the Copernicus is the best tool of the year, right before the whole bad BIOS saga. But basically, we wanted to give people visibility where they had none, right? And so that was the core value of Copernicus. But we knew that, this is a kernel driver. This is just a plain Jane kernel driver. It goes out and it talks to the hardware. It checks vulnerability information, and it checks, grabs a dump of the BIOS so that you can do an integrity check on it. But, okay, a plain kernel module, well, that's subject to all of the normal rootkit type stuff that you can do. So, there's many, many ways that you could subvert Copernicus 1. And so we said, all right, well, we want to take this stuff off the table. This stuff and other stuff. And so before I talk about the other stuff, right, our Smite 'em attack, I have to go through the finite state machine that is the Intel CPU. So when you start out your CPU, you are in what's called real mode. You can think of this like DOS mode. It was back in the day. Everybody could access all memory everywhere. No notion of paging, no notion of protection rings, no ring 0, no ring 3. Eventually, modern operating systems, bootloaders, they're going to move themselves into protected mode. Now you've got virtual memory, you've got protect rings and so forth. There's a backwards compatibility mode over here, and then eventually you can go up into 64-bit mode. But what we're interested in is system management mode, and that was kind of a mode which was very much overlooked for a number of years until 2006, when Duflo was showing, okay, well, I can defeat the security mechanisms of OpenBSD if I just pop into this other system management RAM. So I like this diagram because I'm a child of the 80s, and that reminds me of batteries not included. So recognizing that SMM is and then later on with, the various Invisible Things Labs work, they basically, discussed how SMM is kind of the most privileged execution domain that you can have on the x86 processor. And that's by virtue of the fact that when you're running an SMM, you can see everybody else's RAM, but nobody can see your RAM, right? So it's the best possible place for someone to live if they're an attacker. And they used it explicitly in order to defeat TXT, and we'll talk about that later as well. But we basically said, okay, well, there's all these other normal kind of rootkit stuff that you can do against Copernicus driver in order to make it lie and say that the system's not infected when it is infected. But we knew of this, we like to read the manuals, read the fun manuals. So we knew that there was this other sort of more architectural way that you could basically defeat everything. So defeat everything, don't care whether you boot into a boot CD, I don't care whether you're Linux, whether you're Windows, whether you're Mac, you can defeat everything because there's just architectural mechanisms. And so Smite 'em was this architectural SMM man in the middle, Smite 'em. What it really comes down to, again, we're not going to go through everything in the previous talks, so go back and watch the CanSec West and the Syscan talk and all that. But what it really boils down to for the Smite 'em attack is there exists a register, hardware sequencing flash control register. There's a couple of registers which are going to generally be memory map registers. And if you, as a kernel module or something else, can touch these, then you can do programming of the flash chip. You can read, you can write, and in this case, you can set a bit that says, I want to know whenever the Southbridge, the platform controller hub, I want to know whenever the hardware is done executing a read, or I want to know whenever the hardware is done executing a write. So over here to the side, we've got Copernicus trying to read the flash chip. And over here, we've got a bit where if an attacker sets it, then they get to know every time Copernicus is about to get back some data, they get a chance to go see that data first, right? And that's the essence of the attack. So you've got flash ROM, you've got Copernicus, you've got ChipSec, all of our little kernel ring 0 tools able to touch these memory mapped registers. And how they work is they say, okay, I'm going to set some address that I want to read from the flash chip. So offset hex 1000 into the flash chip. I'm going to set what kind of access I'm going to do. Well, this is 0 for read, 1 for write. I don't remember exactly what write is. And then I'm going to set the data size. It turns out you can only access the flash chip 64 bytes at a time, so that's fun. That means we're dumping 8, 12, 16 megabyte BIOSes, 64 bytes at a time, talking to the flash chip over a 33 megahertz bus. So when Copernicus is slow for you, that's why. And that's why it takes 30 seconds or so. But anyways, they say, okay, set it up. I want to read that location, knock it down. I want to set the fgo bit to say go out and execute this read for me. And then once you set the go bit, then the cycle in progress bit gets set. And eventually, when the hardware is done collecting the data that you've asked for from the flash chip, then the fdone bit is set. And so if and only if this FSMIE bit, flash SMI enable bit is set, then when the fdone is set, it will issue a system management interrupt. It'll go into whatever code is in system management RAM. And that means if an attacker is in SMM, they will have the first opportunity to see this. And the reason why we sort of associate attackers in SMM with attackers in BIOS is because the way that the architecture usually works is you're booting your system, you're loading up the BIOS. The BIOS is responsible for sort of like setting the code, which under normal circumstances, absent an attacker, this would be just code that manages the hardware, things that's sort of supposed to give you sort of a, if you will, a quasi-real-time interrupt ability on Intel hardware. So it's basically saying, all right, I want to know when there's some, special thing that I need to handle like right away, and it needs to be OS independent. It can't be anything that goes through the OS's interrupt descriptor table. I need to like handle some hardware event. The most common cited one is, thermal event, right? The system's hot, SMI, SMM code turns on a fan, SMM done, right? So the BIOS is responsible for putting this sort of vendor-specific code. The vendor who makes your BIOS knows whatever hardware was sitting there on your machine, and they know here's the code I need to put into SMM to handle that. But if someone has infected the BIOS, then they can go ahead and load up their additional code into SMM. That'll be sitting, executing in the background forever. Well, not forever, so I want to be clear. SMM does not like process in the background continuously in parallel with the CPU. SMM is a mode of the CPU, so it's only sort of when an SMI fires, then the existing system halts and you go off to this other code. So it's not running continuously, but there are things like you can set up periodic triggers, you can set up, well, just tell me whenever anyone's accessing the flash chip. So it's still a great place for the attacker to live. So SMI fires, system management mode code, SMITEM, gets a chance to look at the data that's currently stored in the data registers, the flash data registers, and they say, oh, it looks like you're trying to access offset hex 1000. Well, that's where my malicious code in the BIOS exists. So I don't want you to see that. A good example would be if they, just overwrote a bunch of Fs in the BIOS. They'd say, oh, you're accessing offset hex 1000. Well, that should be all Fs as far as you're concerned. And then they just, write Fs back. But I like my hex words. So they found one bad dude, and you've got to write back foosball, which is innocuous. So basically, attacker gets the first opportunity, stick data back into those registers. That's the fun thing about the flash data registers. They're writable, they're readable, writable. And then he resumes the main CPU control flow, and he lets the existing flash readers go and see, oh, fdone is set? Well, I'm going to go read fdata 0 and fdata 1 and fdata 2. And then it'll read in its data, and it will have been lied to, right? That's why we do trust computing research. We don't want software that can be lied to. So the thing is, the interesting thing you might notice here is that All these other bits that got set by the program that was trying to read stuff, they're all in the same register. They're all in this HSFC register, including this FSMIE bit, right? So why does the Copernicus not just set that bit to 0, right? And then you don't have this man-in-the-middle thing going on. Well, that certainly is an option if you know that that's something you need to do. If we hadn't told you about SMITEM, you wouldn't know that's something you need to do, and you'd write code that looks exactly like this. So this is some code from FlashROM, and it's just showing, oh, they're accessing the HSFC register, they're pulling it out, and then they're bit masking off whatever they need to clear, they're bit masking setting whatever they need to set, but no notion of having to do anything with the FSMIE bit. And that's to be expected. But even if they did this, then go read the CanSec West thing. There's obviously other ways that you can still do this trick. You can do race conditions. You can do virtualization-based version of this. So that is SMITEM. And so this is SMITEM versus Copernicus 2. So now I want to explain, how did we use TXT in order to defeat SMITEM? Well, what was the core thing we were going after? So if the attacker is generally going to live in system management mode, because that's, the BIOS runs at the boot time, but then it's done and it passes control to the bootloader, right? So if the attacker who persists in the BIOS wants continuous control, they're going to either need to, jump off to some other parallel processor on a peripheral or something like that, or if they want to be on the mainboard CPU and not be locked out by DMA protections, then they're going to need to be in system management mode. So if we hypothesize that a infected BIOS will also have an infected system management mode, then theoretically we can at least get rid of this man-in-the-middle attack by disabling system management interrupts for the duration of our read of the flash chip. So we're just saying, okay, make sure that no one else can interrupt me and I just want to go read my 64 bytes at a time. So it's not sufficient to just, go ahead and do that from within an operating system. From the kernel driver, that's obviously going to fall back to the exact same sort of problems of someone rootkitting us and making us think that we've disabled it when we haven't actually. So what we need to do is we need to use TXT. And specifically, the thing that we see in the documentation is that the initial launch processor must re-enable system management interrupts which were disabled as a part of the SENTER process. So SENTER is the entrance into the secure mode. So let's learn a little bit about TXT. Let's stop SMIs in their tracks and gain the awesome powers of Copernicus 2. So TXT is what's called the dynamic root of trust for measurement. And what that means is basically, Armin was talking about yesterday how a static root of trust for measurement means you start building measurements right from the very beginning. The code in the BIOS should do some measurements of the system and as it's booting, and then it should pass off to something that's already measured, which should pass off to something that's already measured. Dynamic root of trust says, all right, screw it. I don't care if my BIOS is infected. I want to use special new instructions that are built into the CPU to completely tear down the system into a trusted state, something that Intel defines as okay, well, if I just get rid of all of this other stuff, then I am starting from trusted state and I'll start building myself back up from that. Right, so that's what dynamic root of trust for measurement's about. I like this picture from Invisible Things Labs. And again, Armin he talked about sort of inverted sandboxes yesterday, and I like that term in this context. So this was sort of Intel's kind of first attempt at adding an inverted sandbox to their architecture. There's newer things like SGX, which are coming out, which will be better. But the idea is, okay, you want to launch a trusted operating system. You want to launch a trusted hypervisor. You want to launch just a trusted single application, right? You've got a buggy system, assume it's infected. But using this SENTER instruction, you can basically set it up. You can provide page tables that say, okay, here's what I want memory to look like. Here's what I want you to measure. And then I want you to measure that off CPU. And I want you to stick that measurement off in the TPM so that I can go come along and collect that measurement later, do a remote attestation on it, and so forth. So this is kind of an inverted sandbox. You're basically saying, I want to build up a little nugget of trust, and I can build out from there. But it's basically a hardware-enabled inverted sandbox. So there's a variety of things. This is, I think I skipped over it, but it's called in the Intel manuals the SMX instructions, the safer mode instructions. They couldn't call it safe mode instructions because then they get sued when someone says oh, I used your safe mode instructions and it wasn't safe. So The lawyers made them call it safer mode instructions. There's a variety of them, but the ones that we actually care about are going to be things like capabilities and parameters. That's just like check whether or not my CPU supports this, and SENTER and exit. That's start the trusted environment, disable it. And then there's interesting ones like SM control. This is literally the command that says, okay, I'm done measuring my thing. You can go ahead and turn SMIs back on now. We explicitly don't want to use that. That's the thing that like a normal person would use. That's the thing that a hypervisor would use once they get set up, and then they go ahead and they say, well, now I need SMM to run from now on because I don't want to melt my CPU or whatever. And wake up is just pull all the other CPUs in, get them in on the game. So we're just going to really care about SENTER and SEXIT. So it is time to SENTER the dragon. So this is Copernicus 1 architecture for your benefit. How does it work? Kernel driver. Kernel driver reads configuration information. This is sort of the vulnerability check side of Copernicus. It'll check whether or not your system is locked down, whether or not your BIOS is writable, because if your BIOS is writable, that means someone can come along and break you or backdoor you, trivially without an exploit, right? It's basically just the door is completely open and unlocked, right? That's the first order Copernicus check. The second order Copernicus check is let's go read the contents of the flash chip, and that's sort of where the problem is for purposes of this talk. This is the thing where SMM can interpose on that. So what we need to do is we need to build the Copernicus 2 architecture, and flipping back and forth, you can see that the main difference between the Copernicus 1 and Copernicus 2 architecture are sweet nunchuck skills. So we build it up. You have to do Copernicus 2, you have to have a TPM and you have to have TXT. Good news there is basically every enterprise grade thing is going to ship with a TPM these days. And most high-end CPUs will ship with TXT. Word to the wise, I just realized this like a couple days ago. I bought some like test machines, and I bought like a low-end Core i3, cheapest thing, just so that I could get more machines, so that if I break one, then I'm okay. Lowest end things still do not support TXT, even the lowest end corporate models, enterprise grade models that you might buy. So what do we do? First thing, we use Flickr. Flickr is an open source program out of Carnegie Mellon that does TXT, and it also does the AMD version of it. And the whole point of Flickr is that Flickr starts up a measured launch environment, this TXT sort of trusted domain. And so we just get to basically say, okay, we've got this open source code that we can use, and there's like just a little function which you fill in, and you say any code that you want to run, fill it in right here. And the code that we want to run, obviously, is going to be the Copernicus, BIOS access control and dumping checks. So we run Flickr. Flickr loads up also these things that are called SINIT authenticated code modules. These are sort of the true root of trust in a TXT system. These are signed blobs from Intel. You're not supposed to, but let's say you theoretically threw it into IDA, you would see that it is just x86 code. It's just normal x86 code. But it's basically a blob of x86 code that's signed by Intel. Inside the CPU, they have keys that can verify the digital signature. And so that's how you know that like this thing, which is designed to sort of tear the system down and build it back up, measured, it's it's built into the processor that it's signed by Intel. So first you have to load the blob into memory so that you can point at it when you do the SENTER instruction. Then you have to load the measured launch environment code that you want to run later, and you have to set up some metadata about paging. Go take the intermediate x86 class at Open Security Training to learn enough about paging. And then you have to set up some TXT heap. It has its own notion of heap, but don't worry, there's no TXT heap smashing overflows and things like that. So once you get all that set up, then Flickr will do an SENTER, and that says, okay, CPU, tear it down, build it back up. What happens behind the scenes is the CPU, just the SENTER instruction, you point at the signed blob, that moves itself to, or that gets moved to quote-unquote authenticated RAM. We don't know what that is, but AMD people sort of imply that that's probably cache as RAM inside the processor, because the benefit of cache as RAM is that it's not vulnerable to DMA attacks. So you can do DMA into main memory, you can't do DMA into cache as RAM, so this is like just automatically protected at that point. So that authenticated code module, its whole job is to measure stuff. It measures stuff about the context right now so that you can say something about, is my system sort of set up in a particular way? And then it stores that measurement into the TPM. So you can't do TXT without a TPM. So it stores it into PCR17. In the documentation, it says we hash this plus this plus this plus this, and so you can reconstruct the hashes if you want. And then after it does the environment, it measures the measured launch environment, and that is like the core place that we actually care about. So measure the MLE, and that's going to be our Copernicus 2 blob of code, and then store that into PCR18. And that's sort of like the key point here. You have to store a measurement of the code that's going to run, because that code can be tampered with, and that's fine. My Copernicus 2 trusted code can try to lie, but because it was measured before it ever even got a chance to run, that modified manipulated code will at least have some evidence that we ran manipulated code as opposed to the code we expected. So, not to belabor the point, but the overall point of the TXT version of Copernicus 2 is it's going to build up all the exact same information that the untrustworthy Copernicus does, but in TXT land, it's a low abstraction sort of domain. We don't have operating system calls. We don't have file system access, network access. All we have is sort of the assembly we can write ourselves, right, and a little bit of compiled code. So we go check all of the same registers as the untrustworthy domain, and we build up the same text file of information as the untrustworthy domain, but then we like hash that and we store that out to the TPM. So we can't like convey the actual values. I mean, we could, it would just be too much work. So we can't convey the actual values. We get the values, we hash them, and then later on we're going to get the values in an untrustworthy way, and as long as the hash of the untrustworthy data equals the hash of the trustworthy data, then we're all good. So the MLE does the Copernicus measurements, hashes them into the TPM. Does the BIOS measurement, and keep in mind here, right now, we're in trusted execution, we're in TXT land. We said a side effect of TXT is that it turns off SMM, so there is no opportunity for SMITEM to man in the middle these reads of the flash chip. So now we can read chunks of the flash chip and hash it into the TPM. And that's what we do, and then bam, we're done. Exit, exit out, flicker exits, and then as I said, we just start the Copernicus 2 driver, which is really just the Copernicus 1 driver, doing the untrustworthy measurement and get our data, get a way to verify things. So that was just partially because I wanted to tell you about TXT Copernicus 2, but we'll see, exactly how that will be reused by an attacker instead of a good guy. So now let's talk about Charizard. So amongst the protection mechanism, I'm probably going to go late, by the way, so if you need your coffee, go get it now. Amongst the various mechanisms, there's basically a whole bunch of different mechanisms that Intel uses to protect the flash chip. They started with something very simple and basic, and then over time they added more and more sort of configuration stuff. So the one that we're going to sort of focus on with Charizard is this BIOS lock enable and its sort of interaction with the BIOS write enable. So there's a register somewhere called BIOS control. It's on the Southbridge ICH or Modern Systems Platform Controller Hub. And the way that this works is basically if you set the BIOS write enable bit to 1, then you are allowed to write to the BIOS. Okay, that's simple through that flash interface that we talked about a little bit already. If the BIOS wants to protect itself and it wants to not allow you to write to the BIOS, then it should set the BIOS lock enable bit. And the BIOS lock enable bit doesn't actually just straight up lock you out. It behaves in a sort of interesting way. It's sort of like a soft lock. Because the way it works is I'm some kernel mode attacker. I'm trying to backdoor brick your BIOS. I set BIOS write enable, and the system has properly protected itself and set BIOS lock enable equal to 1. First thing I should say is there's systems out there still which don't set the lock bit at all. So that's like the most trivial possible, come in, backdoor me kind of thing. That's what Copernicus is checking for. It's checking all these different bits. But let's say people are doing the right thing, right? So that's, they're doing the right thing. They're setting the lock enable bit. And if you set BIOS write enable while the lock enable bit is set, it actually causes a system management interrupt rather than just a straight up deny. It's sort of a soft deny. It says, well, SMM code, what do you think? Should they be allowed to write to the BIOS? And so a normal SMM code is going to say, no, they shouldn't be allowed to write to the BIOS. I'm the only one who's allowed to write to the BIOS, and they're not me. right? The instruction pointer is not currently in my code. It's in someone else's code. So no, denied. I'm going to write BIOS write enable back to 0, and then I'm going to resume. And from the kernel mode attacker's perspective, it looks like they just weren't able to set that bit, right? But behind the scenes, there was a decision process that happened with the SMM code. And that's sort of the fundamental problem here, right? So in the interest of time, I'm not going to talk about these other, just had like a couple brief things saying, there's other things like protected range registers. Protected range registers is locked down by flash lockdown bit. Go read the fun manuals, right? I've got links right there, go read your platform controller hub data sheets. But then there's this other more secure version. In newer things, you get an extra bit. You get SMM BIOS write protect, and that says basically, okay, no matter what, you can't, even if you set BIOS write enable legitimately equal to 1, you're not allowed to write to the BIOS unless you're in SMM. So that's another example of how they're sort of pulling back the access controls and saying SMM is our protected domain, and that's who we're going to let write to the BIOS and no one else. So originally, our data set said only 6 out of 8,000 systems had this set. After some patching and we got some more people's data, then we're up to 1,600 out of 10,000. Woo! So only 84% are not using this bit. So by the way, go out and run Copernicus, send us the data please, or run it in your corporate environment, send us the data please. We don't need, there's nothing sort of personally identifiable in there. It's really just, we need more data for more pieces of hardware, because we basically work with the vendors to be like, Dell, lock that down, Lenovo, lock that down. Lenovo's honestly, I don't know if I'm supposed to say this, but the data, you can go check for yourself, right? Lenovo is not doing so good right now for locking things down, but they're getting better because they're starting to work with us. Anyways, so there's a variety of protection mechanisms. So we see that the decision goes through the system management mode code. And so if we could suppress the system management mode code, it would have no opportunity to ever write 0 back to that BIOS lock enable or BIOS write enable. So just looking around through the manuals, we found that there are ways that you can just twiddle the bits in order to say, okay, I don't want SMIs to fire anymore. And that means I don't want SMM to have any voice in the matter of whether or not I can write to the BIOS chip. So we look around and we find there's this bit SMI lock, and it's basically the manual says SMI lock controls this other thing, GBL SMIN, this other register. If SMI lock is not set, then you can write to GBL SMIN. About 40% of the systems we surveyed did not have that set. And then this GBL SMIN is basically a bit that says if it's set to 1, then the south bridge, the ICH, the PCH, the south bridge will generate SMIs. But if it's set to 0, there will be no SMIs ever coming out of the south bridge. And oh, hey, it turns out that the south bridge is the same place that that BIOS control bit is set. So BIOS control bit is the place where you set BIOS write enable equal to 1, and if BIOS lock enable is equal to 1, the south bridge will send a system management interrupt. But this bit right here says no south bridge, you're not allowed to send system management interrupts anymore. And so if you don't lock this bit, you set this bit to 0, and then bang, you just set BIOS write enable equal to 1. So when it's not vulnerable, you set BIOS write enable equal to 1, or sorry, is that, okay. After you disable it, right, then you set BIOS write enable equal to 1 in the control, and it just never fires an SMI. And when you have this ability to just write directly to the flash chip, there's many different things that go on. Again, see the full talk on this topic, but amongst the many things in Intel's Black Hat talk last year, they basically were showing how on systems that didn't have configurations set correctly, you can write to the flash chip. If you can write to the flash chip, you can write to the UEFI variables. There's UEFI variables which are supposed to be authenticated, and like you're only supposed to be able to update them if you have digital signatures, but they're just variables stored on the flash chip, so you can go ahead and smash them and defeat secure boot and do all sorts of other stuff. So with that elaborate setup, with multiple talks worth of information that you need to know before you can get here, Sandman is so very trivial, isn't it? Right? Sandman is doing a Charizard attack using Intel TXT. So we do have systems where they are not vulnerable to Charizard, and they have their access controls set otherwise correctly. They're not using maybe some protected range registers that we'd like them to use, but they're mostly relying on this BIOS write enable, BIOS lock enable, protection duality. So what do? You go out and you grab Flickr, friendly open source project. What do? You write in your assembly into the Flickr pal main function. And when you do that, you load up this TXT world, you've got your measured launch environment, you've got measurements go on. SMIs get suppressed as a consequence of loading the Sandman. And now that SMIs are suppressed, you can go ahead and set BIOS write enable equal to 1. And once you can set BIOS write enable equal to 1, the Sandman can just go ahead and write directly to the flash chip, brick you, backdoor you, and whatever they want to do. So that's the Sandman. And, theoretically, the talk would be done right now, and I'd say any questions. But there's a couple more things that I have to hit on. So, and can someone sitting next to the door close it? Because people are coming through the hall now. So, when I was reading the Intel manuals in order to say, oh, we should do Copernicus 2, SMIs are suppressed in TXT, right? I read the initial launch processor must re-enable SMIs. But, my bad, I didn't read the entire paragraph. I was just like, oh, okay, SMIs are disabled, cool. The paragraph continues, newer CPUs may automatically enable SMIs on entry to the measured launch environment. Well, that's bad from an attacker's perspective because I can't do the Sandman anymore, and that's really much worse from a defender's perspective because I can't do Copernicus 2 anymore. So what are these newer CPUs? Which things are vulnerable here? Which behaves what way? So we start digging through the manuals, right? We look at the pseudocode for the exit authenticated code, leaf of the getsec instruction, of the SMX instructions. We look at the pseudocode, and what the pseudocode is basically saying is if it's not an SENTER, then go ahead and unmask all of those things that you've masked. If it is an SENTER, then if this SMM monitor control bit 0 is equal to 0, then go ahead and unmask. So, all right, well, if we want to do Copernicus 2 or if we want to do the Sandman attack, we need to find a way to not have that be true so that we don't unmask SMIs so that SMIs are still suppressed. So, dig deeper. Where is IA32 SMM monitor control? Well, that's an architectural model-specific register. So IA32 architectural register, bit 0, okay, that's just whether or not the thing is valid or not. Okay, and under what conditions is this, model-specific register even here? Well, you got to call the CPU ID instruction with these flags, and you check these bits. And it's basically just saying, all right, this register is always going to be there if you even support SMX or VMX. All right, so you dig deeper, you look around some more, you try to find information, and there's a whole bunch of interesting things in there. It's basically saying, all right, the IA32 SMM monitor control model-specific register is supported only on processors that support dual mode treatment. All right, other stuff, but another thing, IA32 SMM monitor control is an MSR that can only be written in SMM. Well, that's a problem for us as an attacker or defender. It's saying basically I can't set that bit 0 equal to 1 because I'm not in SMM. That's kind of the whole point of what I'm trying to do. I'm trying to turn off SMM because I'm outside of SMM and I don't want it messing with me. Right, so I can't do that, unfortunately, because I'm not in SMM. So then the question is, who sets that, when and where and why and whatever. But let's focus on, what we're still doing, pull it back up for a second. What we're trying to do is figure out, under what conditions will that bit be set to 1 so that we can keep our precious SMI suppression, right? And so we're trying to find, which CPUs behave which ways and all that. So then we need to dig down on this dual monitor treatment. What's dual monitor treatment? Consult the manuals. Dual monitor treatment uses an executive monitor and an SMM transfer monitor. So, SMM transfer monitor, STM. If you follow this particular domain, which I'm talking about, you have not heard about STMs since way back in 2009 when Invisible Things Labs was breaking TXT. And so first to talk about their TXT boot for, Armin, he was talking yesterday about how they used T-boot in their things, but they used Trusted Grub and they moved over to T-boot. Well, the thing is, even, again, in the full CanSec West talk, we talk about the caveats of our usage of TXT and why it does or doesn't matter. But there's sort of like an architectural vulnerability to TXT usage, right? So you can use TXT, you can build this measured launch environment, you can get a trustworthy nugget of code, and you can build it up. But if SMIs are not suppressed, then the BIOS could have gone out and infected SMM, you start your little trusted nugget of code, And at some point, an SMI is going to fire, and that malicious code is going to go out and compromise your code, whatever trusted code it is, Copernicus 2, Special Zen hypervisor, Linux kernel, whatever. And so Invisible Things recognized this and showed this back in 2009. They said, all right, well, assume you compromise at the BIOS, not the grub anymore, but assume you can get into system management mode. It'll do this measured launch, basically measured launch tboot.gzip. That's basically Intel's open source TXT implementation of trusted boot, where you say, just throw away all the other TPM measurements, or don't throw them away, but I don't care about them. I'm going to make fresh measurements of only the stuff I care about for my little trusted measured launch environment. So I'm going to tboot. I don't care anything that's happened before now. Just start me up trusted, and then bam, you've got a trusted Zen hypervisor started. But the problem is you've got an infected SMRAM off to the side where whenever you get the next SMI, bam, you're now compromised forevermore. So that's a problem. They recognize it's a problem. They talked to Intel about the problem, and Intel said the solution to that problem is called STM. They said, can we look at the STM? They said, nope, there isn't one. And they said, I mean, people can make one, but there's no market demand. And guess what? We're 5 years later, and there's still no market demand, and there's still no STM, so we're still architecturally vulnerable. The architecture has a fix, but it doesn't exist yet. So what is STM? In simple terms, STM is a second hypervisor for your SMM code. So when Intel was adding in this hardware support for virtualization, you do your normal operating system virtualization off on this side. You've got this SMM code that can go compromise everybody everywhere. Best place to be. But they have an architectural fix for that, which is an STM, which is the second hypervisor, which jails the SMM code and does not allow it to go out and touch all RAM everywhere, right? So that's good, except it doesn't exist. So back at the time, they said, Intel told us we have this STM specification. Here you go. There's this doc. You can make it. You can go make your own STM. And they said, no, thank you. We don't want to tie our hands by NDA. And that's fine. I totally understand that. Going with the black box approach is good. We like to be more impactful, more fast. So we said, all right, screw it. We'll accept the NDA. We will get the STM documentation. We will now know how we can fix this problem, even if there's no implementations right now. There's been various proof of concept implementations, but it's a kind of thing where once we got the manual, we were like, okay, goody, let's learn about the STM, because guess what? If you can use virtualization to blue pill a virtual machine, maybe I can use the STM to blue pill SMM, and now I can become more privileged than SMM. So obviously we're rubbing our hands and like, ooh, that's cool. But it turns out you can't just dynamically launch an STM. The STM has to be already sitting around inert in system management mode RAM. And so basically that means the BIOS is the one who has to load up an STM into SMM mode, and then you just have a flag that you set when you do a TXT measured launch that says, yes, I'd like to use an STM, and then that already existing STM can be used. So that is the description of what I just said is in the normal Intel manuals. We got to check out the NDA'd Intel STM documentation, which now 5 years later is at 0.99 version 8. Right? They're never going to release this thing. I don't know what the problem is here, but we keep pushing on them. And if you actually care about having a trusted architecture, how about you push on them too, right? If you have any number of Intel machines, you push on them too. But interesting thing, unlike the government, which has the ability to redact documents, declassify documents, Intel apparently has no way to declassify DNDA documents. So I said, look, there's just this one picture that I need to show people in order to explain to them under what conditions SMIs are disabled versus SMIs are enabled. And they said, nope. So there's your Intel document. There's your correct states. So if you can get right here, bam, you win. SMIs are disabled. If you go right here, sad face, oh, SMIs are enabled immediately upon launch of the TXT environment. But there's basically two places to win, one place is to lose, but nowadays you're going to go to the lose case and you're going to have SMIs enabled immediately starting afterwards. So this way to win, just in case you ever find yourself with access to the Intel NDA document, go that way in order to still be able to do Copernicus 2 and still be able to do the Sandman. But sort of at the end of the day, because the documentation didn't actually have sufficient information to know which CPUs. I mean, It does have enough documentation to know which bits I have to check, but then I need to add that into Copernicus, run it on all sorts of machines, and figure out, which CPUs actually support dual monitor treatment, right? So that will be added to Copernicus, just haven't got around to it yet. But what they said basically is newer CPUs, things that do not suppress SMIs, are Nehalem and newer. And what that means is Core I series and newer. So Core 2s, they behaved with SMI suppression, and Core I's, they do not. And well, Core I's are kind of on their 4th or 5th generation at this point, so that's kind of all of the machines. So that's sad. Miscellaneous fact, turns out that Xeon CPUs do not even support an STM. So if you've got server grade things, you don't even have the option to protect yourself against SMM attackers. They basically, Intel says, oh, well, you're going to use the static root of trust to measure the SMM code, and that'll be good, right? We showed why that's a problem last year at Black Hat. But they do have an improved version of the static root of trust where you can use an Intel trusted execution technology, signed blob, as the actual reset vector for the CPU instead of like starting with the untrustworthy BIOS code. So 601, half dozen of the other problems. So miscellaneous last thing, I said that part of our investigation for this was we wanted to know, we knew we had this idea for the Sandman attack, and we said, okay, well, I don't want it to be the case that I give you Copernicus 2, I tell you, go out, turn on TXT, turn on your TPM, run Copernicus 2, and cool, you've got, secure BIOS measurements. I don't want to be opening you up to the Sandman attacks at the same time, right? So are you automatically vulnerable to Sandman? Well, you are if you don't do anything extra. Basically, there's a mechanism within TXT. This is sort of the appropriate access control mechanism, launch control policies. This basically says you basically are whitelisting which measured launch environments you can load, so which TXT code you can load. And so you can say, I will allow only TXT code that has the measurement foo, which corresponds to Copernicus 2, but I will not allow anything else besides that. And that means you can lock in that Copernicus 2 can run, but you can lock out that the Sandman can run. So there does exist an architectural and appropriately utilizable and actually implemented mechanism to do that. So back to this point, right? Hopefully you can now see, TXT can be used for an attacker. It can be used for more good than bad, but, caveat that. So our final results here are that the Sandman and Copernicus 2 work on older machines that suppress SMIs. And what I didn't say is that one of those little win areas are if a system does have an STM. So let's say that someday we all get together and say, hey, we'd like to not be architecturally vulnerable anymore. We'd like you to start including STMs in your BIOSes vendors. Then in such future world where STMs exist, then SMIs are suppressed, and all of a sudden Copernicus 2 goes back to working again, as does the Sandman. So watch out for it. Keep checking your BIOSes for STMs, right? Can you? No. So that's why you need our tools to actually say, what's there, what's not there. BIOS vendors have to actually include STMs. Like, it's not the kind of thing we can late launch, but that's probably a good thing because, like I said, otherwise, if we could late launch the STM as well, then we could blue pill SMM and become super uber privileged. And unfortunately, we're not aware of anyone who's planning on shipping STMs at this time. Again, we're pushing for it. For people who try to build high assurance systems, we're making sure they push for it. But the key point is where Copernicus 2 has fallen, SMITEM holds court, right? Just right now, today, Copernicus 2 can't give you any extra trust. There is no trustworthy software mechanism for you to check your BIOS, right? So, sorry for the bad news, but the good news is that, we're not blowing smoke and telling you, oh, here you go check your BIOS and, you'll know whether or not there's an attacker there. We're telling you, well, turns out you can't actually know whether there's an attacker there. The good thing there is nobody ever checks their BIOS, right? So why would an attacker actually be incentivized in order to hide themselves, do SMITEM attacks, defeat Copernicus 2, things like that? So you have a limited window of opportunity in which your BIOS backdoors, which are installed on all of your machines, are probably not self-protecting against these things. Maybe not. Again, SMITEM and Copernicus 2 came out back in March, so maybe they've updated it and given you an upgrade since then. But as far as I'm concerned, you have a limited window of opportunity in which to go out, check all of your BIOSes, do your integrity checks, and find out whether or not you have some malware before people get around to adapting. So, main point. We've got 3 different ways now that we described how to defeat this sort of BIOS control, BIOS lock enable mechanism. But at the end of the day, it doesn't actually matter because there's an architectural flaw that we've now found, like an in silicon can't fix it kind of thing, where BIOS lock enable is going to be bypassable. So you have to start, BIOS vendors have to start using these other mechanisms, these protected range registers, this BIOS write protect, and that's kind of what we're doing behind the scenes. We're telling them before these things are public, look, it's coming out, you're going to have to fix stuff now. And they've known about, Intel says they've known about that thing for a while, and that's why they added this other bit, but that doesn't mean that people started using it. So, in conclusion, this is what we talked about today. This is other stuff that we've talked about, other vulnerabilities we've talked about. There's a new thing, and for people in this area, check out Corey, my colleague, and Rafal, formerly of Invisible Things, now at Bromium. They're going to be giving a joint talk at CCC where they talk about 2 new vulnerabilities, the speed racer architectural vulnerability and another vulnerability currently codenamed Plagueis the Wise. Closing thoughts, sleep with one eye open, gripping your pillow tight. Exit light, da-da-da. Enter night. Take my hand, off to Never Never Land. Questions?
Okay, before we start with the questions, 2 short announcements. We've got t-shirts outside, and t-shirts are free for speakers and for the first 50 people who actually fill out a feedback form. So the second talk ended early, so if you want one, get one now.
Oh, well, thanks. Yeah, just run out the door. But also feedback forms to tell them that this was the best damn talk you've ever seen. So.
And after the lunch break, there will also be stickers. And yeah, let's go to the questions.
All right, questions. Yeah, so Armin, you don't need to implement our timing-based attestation because you're using T-boot now. You just need to get people to use STMs. So.
Thank you very much, Sina, for this interesting talk. I don't go into all the many details you've told. My question is more almost political, let's say like that. You said that if Intel would push or ship this STM thing.
Fundamentally, it's not Intel who has to ship one. The issue is it's the vendors because it has to be made appropriate to their particular implementation of SMM code. Right, so they have a specification, and it's NDA'd, and all the vendors have the NDAs in order to get these docs. So all the vendors have the docs. The core issue is they need customers to actually say, hey, we actually want to be trustworthy, because right now no one's saying that. No one's saying, let me fix that.
I want Intel, what I've read, they want to totally push this trusted computing technology. They're writing books, and they're writing software, and all these things. And so... I don't, and this STM specification, you said it's 5 years old,
yeah,
and still more or less it doesn't exist.
So what have we seen
seems,
in the last
for me,
5
it
years?
makes a little bit. What is the English word? Verschwörungstheory, almost. What are you thinking about this?
No, I mean, look at what we've seen in the last 5 years. Back in the day, we had Invisible Thing Labs doing their, one-off proof of concepts, right? And then a whole bunch of nothing since then, right? So what's the motivating factor there? Why should people put the effort into it? Well, we don't see SMM attacks. We don't see BIOS attacks, right? Well, except now we're seeing it, right? So now there should be a motivating factor. That's part of why, we do our vulnerability disclosures is we're like, look, we know what architecturally needs to be fixed. If I can't get people to go out and check their BIOSes, like, I'm telling you there's all these vulnerabilities, but do you think people are running out and like going out and checking their BIOSes? No, they don't care. They don't want to do BIOS patch management. They don't want to, do some extra work here. So I would never attribute to malice that which is, explainable through incompetence, right? So I don't find it particularly conspiratorial. I find it that, it's level of effort that people are not willing to put into things when they're not clear and present dangers, right? Well, maybe we've got some more evidence for that now, but yeah. Any other questions?
Thank you.
Now to judge whether you have a compromised bias that you might get from a vendor?
So actually, yeah, so his question is, can you tell whether or not you're like supply chained and you're like getting it straight from the vendor compromised? Depends on your assumptions. So but what I'll say is that not to a degree of certainty which we like, right? So beyond this, what we're trying to do behind the scenes is we're trying to make a new sort of BIOS metadata standard where we're trying to get the vendors to say like, look, here's the metadata about my BIOS, here's what the layout of the flash chip is, so here's the portions that you should integrity check, and basically get a bunch of metadata, get like a version of the BIOS, like the flat dump of the BIOS, and get them to sign it, put the key actually on their website so we can actually verify that. Right? We know we have signed BIOS updates these days, but they're signed for the benefit of the vendor. They're not signed for the benefit of independent assessment of whether or not they're modified. So once we get to a world, we can do it sort of ad hoc right now. We can say, under the assumption that the BIOS vendor's website is not compromised, I can go pull down a BIOS update from the vendor, and I can decompose the update. Some of them it's easier than others. Some you have to decompress out the copy of the flash, and others it just sort of you run the exe and it drops the flash to a folder. You can use that as sort of your baseline for known good or presumed good, and then you can use Copernicus, our biosdiff.py. You say, here's my presumed good, here's what I just dumped out of my BIOS, do they match, right? So our biosdiff.py goes through, parses the subsections, parses the flash firmware file system, piecewise hashing, and if you have a difference, it'll actually tell you where the difference is. So under certain assumptions, I think you can sort of get to that, but we want to get to a world where it's like machine readable metadata files, which are put up on their website, where people, vendors who do whitelisting, your tripwires, your bit9s, we want vendors who do whitelisting to start doing BIOS whitelisting, but we want to make it easier for them to do that so that they don't have to put so much money into it. So if the BIOS vendors just give a little bit of metadata, which can be mostly programmatically generated at the time that they're generating their BIOS, and then slap that up on a website, the tripwires of the world pull that down and can, have an assessment against that. So not as good as we'd like it right now, and we're trying to make it better. That answered your question? All right. Other questions?
Other questions?
All right.
Okay.
See you outside.